Hi all. Hope you are staying at home very safe without going out even after the curfew is lifted. Better stay at home for security and safety. Alright, so we will discuss about more on AC circuit analysis today. Last week or last lecture we actually discussed about the basics on AC contents, that is like how the capacitors, inductors are behaving, and the introduction to the impedance, reactance, and things like that. So today actually I'll be running a little faster because the topics that we are talking about today are the Kirchhoff laws, the Ohm's law, circuit analysis techniques like mesh analysis, nodal analysis, and then theorems like superposition, Thevenin's, Norton's, maximum power transfer, those things. But because you already know the basics behind all these techniques and theorems, we will be looking at how we are going to use the techniques in AC circuits. You have been using them for DC circuits without much of a trouble. So now you know what those principles or techniques and theorems do. In the today's discussion, we will be talking about how to use them in AC circuits. Right, so I'll be going a little faster because you know all the steps steps that you have to follow and so on and so forth. But the main intention in this discussion today is to look how we can use AC theories to solve the circuits. So the reference chapters are chapters 18 to 20 in the reference book. So yeah, this is what actually I was talking about. We can use methods that were used in DC circuits, but little differences and limitations when it comes to AC analysis. So phasors are represented with their RMS values. So we will be working basically in the phasor domain, right? Instead of DC domains, all techniques that were used in DC analysis will be now used with AC analysis, for AC analysis with all phasors or in RMS values, right? Let's look at now the Ohm's law. When it comes to Ohm's law, previously with DC we had this Ohm's law relationship. V is equal to IR, or I is equal to V over R. Now instead of R, in the case of AC we will have Z, the impedance. However, for resistors, impedance is with zero angle. We know that R angle 0. So therefore the current is also having an angle of 0 if voltage is having an angle of 0. So voltage and current are in phase. This we actually saw in the phasor diagrams as well, but here it is not the phasor diagrams that we are discussing. How to use that knowledge in the AC analysis is what we are talking about here. So mainly in the phasor domain, the current will have the same phase angle as the voltage. You can see the waveform. These were actually available we discussed this in the previous lecture as well. Now for inductors, because the inductive reactance, last time we discussed that it is having a phase angle of 90 degrees, so that's plus J. So JXL, if you put it in the complex number domain, it will be V, whatever the angle that it has, divided by JXL or XL angle 90. So therefore it will add a minus 90 degree phase shift to the whole current. So in the case of inductors, the current is lagging by 90 degrees to the voltage, whatsoever the voltage is. Last week we looked at that in the phasor diagram means, but now it is the equation means. For a capacitor, it is other way around, because the capacitive reactance is having a phase angle of minus 90. The current will be having a phase angle of plus 90 with respect to the voltage. So current is leading by 90 degrees to the voltage, right? So this is XC and XL. When it comes to complex, it will be J XL, J omega L, and XC is 1 over J omega C, or minus J over omega C. We'll discuss this when we come into the examples as well. So series and parallel case, this is how it is. This is just what I have discussed earlier, right? So XL is Z impedance of an inductance is JXL, impedance of a capacitor is minus JXL, resistance is simply it's R. Series, you can simply add the impedances. Last week also we discussed this, have added this as a completion. And for parallel, we, instead of adding impedance, we add the admittances. So total admittance is the addition of admittances. So admittance is 1 upon, or the reciprocal of impedance. So 1 over J is equal to Y. So that is what is shown in here. So once you find the reciprocal of each component, or admittances of each components, you can add them together, rather than using the parallel impedance equations or something like that, because when now this is complex, we have to work with the phasors and complex numbers. So therefore it is easier for us to work with admittances rather than using the parallel impedance equation. So that is why we do that, but it is actually essentially the same. You can see that if you substitute the z's in this equation, it is 1 upon ZT is equal to 1 upon Z1 plus 1 upon Z2, and so on and so forth. So it is essentially the same, but for easy operations, easy use, admittances are used instead of impedances. Right. So for an example, find ZT. Sketch the impedance diagram for the network and indicate whether the total impedance of the circuit is inductive, capacitive, or resistive. Use Ohm's law to determine I, VR, and VC. So let's take this. Right, so what we have to find is ZT first. So ZT is equal to, that is the total impedance, ZT is equal to, this is 25 ohms, this is J200, and ohms, this is minus J225. So the total is 25 ohms minus J 25 ohms. Now to do these calculations you will have to switch to the complex number mode in your calculators. In there you can convert the polar coordinates into the Cartesian coordinates or Cartesian coordinates to polar coordinates. You must see something like an arrow r theta or arrow x plus y I, something like this somewhere in the keyboard. Please refer keypad, please refer to the manual of your calculator to find out how to do these things. So with using this you can convert the polar coordinates to now this is to convert the Cartesian coordinates to polar coordinates, and this is to convert polar coordinates to Cartesian coordinates, right? So let me take my calculator. Now if you have any issues in using the calculator, you can first you refer to the manual or the user manual of your calculator, and then if you still have issues you can post those in the WhatsApp group. So 25, as I said in the last week lecture as well, last lecture as well, now you don't have J in the calculator, instead you have I in the calculator, and you have to enter the key sequence like this. You can't actually enter the sequence like this 25 minus J. Instead you have to enter 25 minus 25 I. This is when you use the calculator, right? Using the calculator, this is how you have to do that. So I'm going to do that. 25 minus 25I equal, then I can convert that to r theta. This gives us I'll use red color, 35.35 angle minus 45 degrees. Be careful to be in the correct angle mode, degrees or radians or gradients. We use degrees or radians, so be careful to be in the correct angle domain, right? So this is 35. This is using the calculator, right? I converted it using the calculator. You don't have to worry about it. Better the only thing that you need to do is to find out how to do this in the calculator, right? So that's that. Then we have to find I, right? Capital I in the complex number domain. So this is in the complex number domain. All these values are in the complex number domain. So Z was found. Then I, right? I is equal to V over ZT. So V is equal to 10 angle 0 degrees divided by ZT is 35.35 angle minus 45. They have asked us to do something else, right? So impedance diagram, sketch the impedance diagram. So the impedance diagram is you have the that has to be vertical. So this is our impedance diagram, right? And our impedance is magnitude. That is why actually I wanted to find this, right? That's okay. The angle is minus 45 and the magnitude is, this is minus 45, so 45 degrees. 45 degrees, and the magnitude is 33.35, right? So that's our impedance, so ZT, right? That's our ZT. And now in here, actually, because you found this one, you can do this, or alternatively I'm using a different color for that. 10 angle 0 degrees divided by what you found here is 25 minus j 25, right? So be careful with the the volts and things like that. So this is volts, this is ohms, so this is volts, this whole thing is in ohms, so your current would be in amperes, right? So now in this case you can divide 10 by this, and angle will be 45. So because I don't have that with me, what I do is I'll use the calculator to divide this 10 divided by the answer. Right, so what I get is 0. Now I get two answers actually. What I get is the Cartesian form. It is 0.2 plus 0.2 j 0.2, right? Or else if you convert that into the polar, what you get is 0.28, this is amperes, right? 0.28 amperes, angle 45 degrees, right? So use the calculator to do all these stuff without trouble. So I is calculated. What else do we have to calculate? VR. So once you know I is the current that goes to the entire circuit. So R is VR is I into R. Now R I did not mention as a complex number because it's a scalar in this calculation. So that is, either you do this, right, 0.2 plus j 0.2 into R is 25, right, amperes, 25 ohms, or you can write it as 0.28 amperes, angle 45 degrees into 25 ohms. Both these will give us the same answer, so that this multiplied by 25, you get 5 plus 5 j5 volts, or in the Cartesian form you get 7.07 volts, angle 45 degrees, right? So that's V. What about VR? VC, the same equation we can use for VC. VC is equal to I into XC now, right? XC. So that is 0.2 plus j 0.2 amperes into XC. What is XC? XC is minus j 225 into minus j 225 ohms. So let's do this and see. So we'll need brackets, so that is 0.2 plus 0.2 I. I'm telling the sequence that has to go with the calculator. multiplied by, put a bracket, minus sign, 225i, right, equals to, what we get is 45 minus 45 J45, right, or as polar coordinate, polar value, this is volts, 63.63 or 64 rather, 64 volts, angle should be 45, minus 45, minus 45. Is this correct? I think I have done a mistake here. Let's check. 0.2 plus 0.2i multiplied by, yeah, this is correct, because this rotates it by 90 degrees, so it's correct. So minus 225 I, so it's 45 degrees. Okay, so 45 minus J45, or 63.64 volts minus 45 degrees, right? So that's what you can see here, right? All the answers are again shown here, right? Now find the equivalent admittance and impedance of the network of the figure. Sketch the admittance diagram in here. So I'm not going to do actually this again because the answers are available in the PowerPoint. We will look at how to do that. So all impedances will have to be converted into an admittance. So here the impedance is just 40 ohms, angle 0. So 1 upon that is admittance. Y2 is this one, so it is 60 angle minus 90. So that is converted, taken, the reciprocal is taken, so that is this. And if you convert this into, again, y1 upon 30 ohms, angle 90 degrees, we'll get this one. So when you add those together, all the three together, because yt is equal to y1 plus y2 plus y3, so it's the addition of these three, right? So yt is equal to 30 millisiemens, angle, because 1 upon ohms is in Siemens, millisiemens, angles minus 33.63. You can use the calculator to do all these calculations. And if you want to find the impedance, total impedance, it is 1 upon yt, which is 33.3, angle 33.96. So the admittance diagram is what you show here. It's just the angle and the amplitude is shown, right? So now when it comes to voltage divider, Kirchhoff's voltage law and the voltage divider, as well as Kirchhoff's current law and the current divider, instead of resistances, here we will be using impedances, right? So there is no other difference than that. So Vx earlier was equal to Rx divided by R total into E. So here instead of R we have Zx divided by Zt. So both all these figures in this equation, this is in the complex number domain, this is in the complex number domain, all these four figures are in the complex number domain. So instead of resistances we have impedances, all the parameters are with a magnitude and a phase angle now, right? That's the main difference that we have from DC to AC. Other than that, you just follow the same procedures. So in the current divided rule, again the same. So if you want to find the current across a certain device, what's there is the equation that is shown here. So yx over yt into I, right? So that will actually simplify into this equation where you have the other impedance divided by the total impedance. If you substitute the values in here, because yt is yx is the particular one, yt will be z1 z2 divided by z1 is plus z2, that divided by z2 z1. If you want to find across z1, it will be it will cancel out z1, so it will give you this equation, right? Right, the frequency effect, as you got to know last week, the reactance is a frequency dependent parameter. So therefore, whenever you have a capacitance or an inductance or both, the behavior will be frequency dependent. So therefore, we will have to consider a given frequency, or the analysis will be performed for a given frequency. The behavior of variable frequencies is discussed in chapter section 18.7 of the reference book. You can refer to that to understand how the effect of the variable frequency would affect the performance of a circuit. But for the scope, we are not talking about that. We will be talking about the constant frequency. So once you calculate the impedance for a given frequency, we will be doing the analysis only for that particular frequency, right? Most cases there is a possibility that the reactance is given, as we saw in these equations. This is actually the reactance what is given, so that is why it is in ohms. So it's for a particular frequency, right? But if the capacitor value is given, you will have to be we will have to know the frequency as well, so the frequency will also be given. Then you can calculate the reactance using the reactance equations that we discussed last week as well as today, last lecture as well as this lecture. So series parallel conversion we were talking about. Okay, no, not this one. So if you have a series connection, resistance and a reactance, and you want to convert that into a parallel connection for some reason, the resistance and the same thing in here, or a parallel reactance in here, these are the equations that you use. So to convert from parallel to series, look at this. So if it is a resistance comes at power 1 and impedance goes at power 2. For impedance, it is the resistance power 2 and impedance power 1. In the denominator, you have the resistance squared plus impedance squared addition. Now this is in the scalar domain without j. So if this is an inductance, this will also be an inductance. If this is a capacitance, this will also be a capacitance. So in this both vice versa transform, it will be like that. So if you want to convert a series to parallel, the parallel resistance will be this squared plus this squared divided by the resistance. So in the case of parallel impedance, this squared plus this squared divided by the reactance, right? So that will give you the reactance. So in this example, simply it's just a matter of using the equation, right? So parallel resistance is given by this squared plus this squared divided by this, so it's 260. And parallel inductance is again this squared plus this squared divided by 50, so it becomes 52 ohms. So 260 ohms, 52 ohms. So this is how you convert a series connected reactance and a resistance to a parallel connected resistance and a reactance. Then the source conversion, same relationship. Instead of V is equal to IR or E is equal to IR, we have E is equal to IZ. Now all these parameters are now in the phasor domain or the complex number domain, because they are having an amplitude or magnitude and a phase angle, right? Nothing other than that. So we'll have to use the complex number domain in the calculator for these calculations, and all these values will be in the complex number domain because they have a magnitude and a phase angle. Again, I'm reminding the point that there is no imaginary current values or voltage values. They are very real, but because they have a phase angle to be represented, we use the complex number domain, right? Now the conversion from parallel from a voltage source to a current source. So the impedance goes as it is, as we already know, and the current is ZT is given in here. Now in this case, of course, you can simply use whatever exists. So I is equal to 10 volts angle, or 10 volts angle 0 degrees divided by, don't worry, the calculator will give you the answer, 3 plus J 4 ohms, right? 3 ohms plus J 4 ohms. So simply enter this, or simply enter 10 divided by 10 divided by 3 plus 4 I to the calculator. This will give you this answer, right? So you don't have to always convert whatever the value into a polar value or Cartesian value. Use that as it is. If it is given in polar form, use it in polar form. If it is given in Cartesian, use it as Cartesian. However, in the case of representation, generally sources are represented using the polar form, because in that case it is easier to identify the magnitude and the phase angle of the source. Magnitude and the phase angle of the source. However, when it comes to impedances, we prefer to keep it, although it is not necessary at all, we prefer to keep it as a Cartesian, in the Cartesian form, so that we can actually distinguish between the resistive component and the reactive component. This is not necessary at all, but it is easier for us to understand the behavior of the circuit, right? Not mandatory though. So if you just keep the impedance at like 5 ohms angle 53.13 degrees, that's good enough, right? But we like to keep it as a Cartesian, in the Cartesian form, so you can clearly see this is resistive and this is reactive. Okay, now this is current source to conversion from current source to a voltage source. In here something else has also been done, that is okay, let's take this and see, right? Keep so Z, right? So what's Z? Z is equal to R R parallel XC. So that is 40 into minus J20 divided by 40 minus J20. Now I'm going to enter this into the calculator. 40 into minus 20I divided by brackets, so it's not minus, divided by brackets 40 minus 20I equal, what you get is 8 minus 16 J16, right? 8 minus J16, right? So that's what you got here, 8 minus J16. Then you can use that to convert the current source into a voltage source, right? So that's simple. You just divide 240, leave aside the milli, or if you want to, you can enter as 240 e to the power minus 3 or 10 to the power minus 3 angle 30 divide by this 8 minus J60, right, or 69. Then you get this value, right? So what I showed here is in the workout sheet. It is not necessary for you to work out this in the polar form. Just use whatever you have there, you will get the answer, right? You don't have to convert back and forth between polar and Cartesian, right, or Cartesian and polar, right? Just enter the values that you are given. Ultimately you can convert your result into either Cartesian form or the polar form, which is preferred, right? As I said earlier, impedances, reactor impedances and admittances, we prefer to keep it as a Cartesian coordinate value, and sources we prefer to keep them as polar form, in the polar form. Okay, now the steps are given in the section 19.3, right? For the steps are as same as the steps that we followed in the mesh analysis in the DC circuits, right? The only difference is that now we are solving everything in the complex number domain, because all these parameters generally would have magnitude and a phase angle, right? So this is J4, capacitor is minus J3. So all these values are in the complex number domain, right? So that's what we have to consider here. Okay, first thing now we have to do example, solve the loop equations in the circuit of the figure below, right? So we have a voltage source here and a series impedance. There is no drama there, is no much difference there, but here this one we will have to convert it into a current source. So I am not going to discuss that conversion in the workout sheet. So this conversion is done because we have already done a conversion previously. However, I'll be starting from this point and doing the rest, right? Or one more step, we can actually convert this, right? So we have a impedance here, right? This is one impedance, and this is another, right, and this is another. So three impedances. We can treat this as an impedance, of course, in generic terms. So we can again now convert the circuit, just a matter of representation for easy operation, right, to this, right? So z, in that case z1, okay, z1 here is what is z1? 3 ohms minus j3 ohms. Z2 is 1 ohm, j0. Z3 is 2 ohms. So I'll write those things, right? So this is 2 ohms plus j4 ohms. This is 1 ohm plus j0. This is 3 ohms minus j3 ohms. Why minus? Is because this is a capacitor, right? So now you get this circuit, and we will have to mark the plus minus signs in here, right? Plus, because the current goes that way, minus, plus minus here, plus minus, plus minus. That will give us a help, right? So I'll take this one, and let's work out outside. That is easier, right? That's easy to write. Okay. Page. Right. So this is our circuit. Again, I'll mark the voltages. We'll use red color for that. I'm going through the again, right, current directions, clockwise currents are marked. Note that, look at this, this is complex. Now this is a complex number, this is a complex number, this is a complex, this is complex, this is complex, and this, all these parameters are now in general complex numbers, right? So let's mark the voltage drops. I'm going along this current, plus minus, plus minus, plus minus, plus minus. Now let's apply KVL to the first loop. KVL to loop 1. If you apply KVL to loop 1, we get minus I1 Z1, minus I1 Z1, minus E1, minus I1 Z2, plus I2 Z2 equals to 0. Right, let's simplify this. So we have okay, E1 can go to the other side, and minus Z1 plus Z2 I1 plus Z2 I2 equals E1. So this is my equation number 1. Let's substitute the values little later on, right? So KVL to loop 2, you get what do you get? Minus I2 Z2 plus I1 Z1 minus I2 Z3 minus E2 equals 0. So from this you get E2 can go to the other side. So I1 is at 1, I1 is at 1 minus, okay, let's write it as Z1 I1 minus Z2 plus Z3 I2 equals E2, right? So that is equation number 2. Now from equation number 1 we will substitute the values, z1 plus z2, so that is minus z1 is 3 minus j3 plus z2 plus 1 I1 plus z2 is actually 1, right? 1 times I2 equals E1. E1 is 5 angle 0. 5 angle 0. So angle 0 you can leave aside. So this will give you minus 4 minus j3 I1 plus I2 equals 5. The second from the second equation z1 is from the second equation z1 is what is that? Z1 is 3 minus j3 I1 I1 minus z2 plus z3 is I'm going to do that at a stage, right? So that is 3 plus j4 I2 equals again 5. Right, now you have two equations, two unknowns, right? You can use the determinant method to simplify this. So capital D is equal to, well, D is actually in the complex number domain now, equal to, right, minus 4 minus 3j, right, 1, this is 3 minus j3 minus 3 plus j4, okay, which is equal to this into this, that is 4 minus j3, minus minus cancels out, into 3 plus j4 minus 3 minus j3, right? Now you can find the answer using the calculator. Bracket 4 minus 3i bracket 3 plus 4i bracket minus bracket 3 minus 3i equals, okay, I got a value. D is equal to 21 minus j10. So that's D. Now what is I1? I1 is, you replace the coefficients that divide by D, right? So replace the first column by the two constants, those are 5 and 5. So 5 5 1 minus 4 3 plus j4 divided by D. So that is equal to minus 5 times 3 plus j4 minus 5 divided by 21 minus j10, which is equal to minus 15 minus 15 plus minus 15 minus 5 is minus 20, right? Minus, you can use the calculator if you wish, but I'm doing it by hand. Minus 20 j, so j20 minus j20 divided by 21 minus j10. So that's minus 20 plus 20i divided by brackets 21 minus 10i, which is, I'll convert that into Cartesian, or rather polar. 1.216, so 22 amperes angle, 109 minus 109.5 degrees, 0.5 degrees. That's I1. I2, when it comes to I2, you will have to replace the second line now, second column now. So it's minus 4 minus j3, 3 minus j3, 5 divided by d. Right, now you see simultaneous equation. To simplify simultaneous equations, rather than using substitution method, the determinant methods will become very easy or handy when we deal with the AC circuits. That is why we actually learned the determinant methods rather than using that in the DC circuits. AC circuits, that becomes much easier. So this is minus 5 into 4 minus j3 minus 5 into 3 minus j3 divide by 21 minus j10. So let's use the calculator to do this. Minus 5 into 4 minus 3i minus 5 brackets 3 minus 3i, that is minus 35 plus 30 j divided by 21 minus j10. So this answer divided by, oops, so that's, yeah, that divided by brackets 21 minus 10i. So you get, I'll convert again that into Cartesian coordinates, or rather polar coordinates. 1.98 amperes angle is 164.86 degrees. So that's our answers. So let's see if we have got those answers in here. Right, so all that is there. Right, so they have actually gone ahead with the algebraic equation, but I prefer to substitute them. It's up to you, right? Substitution, after substitution, entering becomes easier in some way, right? So okay, our answers were, a little different, right? Might be I have done a mistake, right? Double check those, right? Maybe I have done a mistake there. they have not found D though. Right, maybe I have done a small mistake somewhere in here. Anyway, you can double check if these answers are correct. I'll also go through this later on and put the correct answers in this, but the sequence is the same, so there is no difference in the sequence, right? So if you do it correctly, you will be getting the correct answers. I think I have done a mistake in J, rather D. What the D that I have got is 21 minus J10, whereas they have got 23 plus J. So let's see if I have done a mistake here, right? Okay, 1, right? So Z1 plus Z2, Z1 plus Z2 is these two, so that is 4 plus 4 minus 3J, that is minus, plus Z2 is 1, okay, 1 and 2, this is correct. And here I have Z1, which is 3 minus 3J, minus Z1 plus Z2, that is this plus this. Have I done a mistake there? No, I guess not. This is I2, this is I2. So that's 3 plus J4. It's also correct. So what has gone wrong here? Let me check. So this is 1, this is 3 minus let me enter the values again. So minus and minus, 4 minus 3J, 3 plus 4J, minus 3 minus 3J. So let me check that calculation again, right? 4 minus 3I bracket, let's multiply it by 3 plus 4I minus brackets 3 minus 3I, which is 21. Oops, it becomes plus 10. How can it be? Okay, something is wrong, right? It's actually okay. Let me enter that value again. 4 minus 3I, 3 plus 4I minus brackets 3 minus 3I, 21 plus 10 plus 10. So that's plus 10, that has to be plus 10, that has to be plus 10. So in that case this answer is little bit different. So let's take that answer again. So that's minus 20 plus 20I divided by brackets 21 plus 10I. What I get is 1.21, 22 actually, 21622 angle minus 160 degrees. So it's the same thing, same mistake I have done in here. I'm still it's a different answer that I get. I don't know why. Let me check it later on after finishing the lecture maybe and put up the correct answers. So it's minus 35 plus 30i divided by 21 plus 10i. So it brings me to 1.98 amperes angle 114 degrees, right? So let me check these answers again. Maybe I have done a mistake somewhere, right? So these answers are little different from what I have got here, so I'll check that. They have got 3. Oh. 3 minus. Okay, anyway, so let's leave it at this point. There. So just be correct in the answers, right? So nodal analysis, here I'm actually not going to derive the equations, but I would like to go through the slides here. So given the circuit now of the figure, write the nodal equations and solve for the nodal voltages. So you have a circuit that is having 2 current sources. Note that this is in the complex number domain, this is in the complex number domain, so these two becomes imaginary values because we have to have J2 minus J4. So the entire circuit will have to be solved in the complex number domain. So first thing is to identify a ground node and mark it. Then you identify the other 2 nodes, and V1 and V2 are marked. As you can see, all the resistances, reactances are now represented by admittances in here instead of impedances, to make the analysis easier for nodal analysis, because now the voltage will be I V divided by Vy will be I. So what we want to write is for I, so it's Vy. V divided by Z, but it is Vy, right? Z is 1 upon Y, so Vy. 1 upon Z is Y. Let's look at that. So you mark the 2 nodes and then the currents. That is where we start, and you apply nodal equations. So KCL to this point. So if you apply KCL to this point, currents coming in on this side, so currents coming in, let me write that equation and bring it to here. Okay, right, so first equation will be currents coming in is I1, right? I1 equals, right, currents going out, that is IA plus IB. IA is equal to V1 Y1, V1 Y1, because V1 over Z1 becomes Y1, because 1 over Z is Y. So V1 Y1 plus IB is V1 minus V2, all now in the complex number domain, not divided by, into Y2. Right, so likewise you can write the KCL equation for the second node as well. IB is coming. IB equals IC plus I2, right? So that is IB is equal to again V1 minus V2 into Y2 equals IC is V2 Y3 plus I2, right? So that's the two equations that you have here, and you simplify it using determinant methods, substitute the values and so on and so forth. You actually end up with the two voltage values. So once you know the two voltage values, you can actually simplify the rest, right? So yeah, so you can easily go ahead with the calculation of the currents and all other required parameters for the circuit, right? One thing I forgot, I'll come soon. Right, so the y to delta and delta to y to delta and delta to y, you were actually working with these circuits, right? So I mean for resistive circuits, but now we will have to do that in the complex number domain again, right? So the same equations, but instead of resistor values you have the impedance value. So look at just look at the pattern here, right? Z1 is you have to multiply these two, right, and divide by this plus this plus this, right? To find out Z1, you have to multiply these two, divide by the sum of the three. To find out this, you have to multiply these two and divide by the addition of these three, right? On the other hand, to calculate this one, let's say ZA, what goes on the top is you multiply this into this, this into this, this into this, that divided by the one in the front, so that is Z1, right? To calculate ZB, again what goes top is the same, Z1 Z2, Z2 Z3, Z3 Z1, divide by Z2. Z3 ZC is calculated in the same way. So Z1 Z2 divide Z1 Z2 plus Z2 Z3 plus Z3 Z1 divide by, now what we want to calculate is Z1, so the impedance connected to the opposite node, that is Z3, divide by Z3. So that is how the how these things are going on. Okay, right? So if these three are equal to each other, right, from this you can see now Z1 is the y, right? So if all the z's are equal, this becomes z square or z delta squared divided by 3z delta. So it will actually bring us to a equation that if these three are equal to each other, which is the case of a three-phase balanced circuit, so balanced impedance, these three are equal to each other, then one of the all these three will also be equal to each other, which is equal to this divided by 3. Same way, if these three are equal to each other, so what will be z squared, 3z squared divided by z, or 3zy squared divided by 3zy. So zy cancels out, so 3zy is the answer. So if these three are equal to each other, each of these will be equal to 3 times of this, right? So that you can easily derive from this equation if these are equal to each other. All these three are equal values, right? So you can use these equations to convert a Y connected load to a delta connected load, right? So this is the example. This is an example. You simply use the equation, nothing but using the equation. So once you use the equation, you substitute all in the complex number domain, and you will get the three impedances, Y impedances. So determine the Y equivalent of the delta network in the figure, right? So you can do that with the calculator. Now the superposition theorem, the same again. Superposition theorem says the same thing. I'm not going to actually do this again on the whiteboard or the write up. So it's the same thing that we have to do, right? Now in this case you have to consider each source at a time, but the calculations will be done in the complex number domain, because in general all these parameters are having a magnitude and a phase angle, or they will have imaginary components. Imaginary number domain is what we have to, or complex number domain is what we have to use. So in this case, if you remove if you consider only V, the voltage source, this is removed, so there is no effect from this side. So the current here is V divided by this plus this, the total impedance. So for you can simply, that is what you have written. They have written here V, that is 5 angle 0 divided by 4 minus 2j or j2, right? So you don't have to actually go for this step. You just enter this value to the calculator, you will get this answer, right? So that is I1. I2, you will remove this, and then the current to this will be actually 2 amperes, right? So once you remove it's you have to use the current divider rule, because when you remove the voltage, this will be short circuited. So there is a current division happening between these two. So 2 amperes comes here, that is divided between this and this. So what should go there is current division rule. 4 ohms divided by 4 ohms minus j2. So 4 divided by 4 minus j2 into 2 amperes. So current division rule, you get to I2. So the superposition theorem says now it is applicable to the complex numbers, or it will, the superposition theorem will have to be applied in the complex number domain. So it is I, the total current, is equal to I1 plus I2, right? So this will give us 2.91 amperes angle 26.56. So that was superposition. Thevenin's equivalent, instead of a series resistance, now we will have a series impedance. So all the things are now in the complex number domain. That is the only difference. So same procedure you follow. If you are supposed to convert this or find the Thevenin's equivalent excluding ZL, what you do is you remove ZL, right, and then find the Thevenin's equivalent for this, right? So you remove this first, and when this is a voltage source, so it is a short circuit. So to find the Thevenin's impedance, you need to find this parallel this. So R parallel is it. So you have to simply use the equation. So this is okay. One thing that I would like to write in here is this was actually discussed in the last lecture as well. When it comes to ZL plus ZC is equal to J80 ohms minus J60 ohms, which is J20 ohms. So Z Thevenins now is Z Thevenins is equal to R, that is 40 into J20 divided by 40 plus J20, right? If I do that calculation, so 40 into 20i divided by within brackets 40 plus 20i, which will be 8 plus 16j plus j 16 ohms, right? So you get the same answer. Simply, you don't have to go across or go through any of these tedious steps. You just type into the calculator or write whatever you have there. You don't have to convert back and forth the values between Cartesian and pole, right? So that's Z Thevenins. When it comes to voltage, you just measure the voltage here. You have 3 impedances in series, so the voltage here will be the voltage division. So the 40 divided by 40 plus J80 minus J60, right? Again, you don't have to go to this step, right? So from here you actually get okay, so from here you get VAB is equal to 40 into 20 is 800, right? Or let's keep it as it is. Come on. Okay, this. So it'll be 40 into 20 divided by, you get here 40 plus J20. So if you enter this into the calculator, you will get the value. So it's actually the previous value that you got, right? Yeah, 40 into 20, it's the same thing that you have. That will give us 17.89 volts, angle 63. Forty into 20 divided by, within brackets 40 plus 20i, which is converted to that 17.89 angle minus 26.57, right? So you get it. You can, without going into this step, you can actually do this like this, right? So there is no harm in doing that. Norton's equivalent, the same way, except that you need to use the impedances in here. You have to perform the calculations in the complex number domain, and if you know the one of these, so Thevenin's equivalent, you can convert that into Norton's equivalent. If you know the Norton's equivalent, you can convert that into Thevenin's equivalent using source conversion. Example, find the Norton's equivalent. So the steps are there. You first remove the source, remove the load, right? Once you remove the load and then remove the sources, it's the same circuit that we are having. It's the same impedance therefore, and the current is you create a short here and trying to find the current here. So when you try to find the current here, it is actually the current through these two impedances. So it's 20 divided by J80 minus J60, right? So you get that. You don't have to go through this step again. As I have said, so you just do this. You will get, you just divide 20 by J20, right? You will get 1 ampere angle minus 90, right? One angle minus 90. So it's just a matter of using complex numbers in here. Solution is this, and you can then do any calculations as you wish, right? So that's all for today. And again, I'm reminding, although I rushed through, if you have any issues, any concerns, you can always post that to the WhatsApp group. Also, you can table them in the face-to-face online discussions that we are going to have in the next week as well. So it will be continuing. Well, we can have it even in the New Year week. There is no harm in doing that, right? You are at home, we are at home. If the curfew is there is no issue in conducting them, right? So we will continue that. Until we come into some saturation point, or that is all have sorted out. All the students have sorted out all the issues, or until we start the campus again after this pandemic disaster, right? So I'll stop at this point, and I'll actually go through the answer that I have written in the example, which I found it different, or some error was there. So I'll go through that, and I will update it, and I will publish it. So till I talk to you with a new lecture next time, be safe, be home, be safe, and work well. Alright then.